The final transfer function that we have to consider is a transfer function that has a pair of complex zeros. And this transfer function looks something like this. T of 8 of s is equal to s over omega b squared plus 2 zeta s over omega b plus 1. Okay, just like in the previous case, we can rewrite this as 1 over 1 over s over omega b squared plus 2 zeta s over omega b plus 1. Okay, so what we are in effect doing is we subtracting the transfer function of a constant and dividing that by the transfer function of a constant and dividing that by the transfer function of a transfer function that has a pair of complex poles. So this is just a transfer function of a constant, and this is a transfer function as a pair of complex poles. Okay, and because we're plotting in the log domain, we can just subtract the frequency response of the transfer function in the numerator we can subtract the transfer function in the denominator from the transfer function in the numerator. Okay, and like in the previous cases, we can show that the frequency response of this overall transfer function, which in this case is just a transfer function that has a pair of complex zeros, is just a reflection about the frequency axis of the frequency response of the transfer function as a pair of complex poles. And just to quickly show you how that looks. Let's quickly draw our Bode diagrams. So let's first draw the magnitude and phase plots for a transfer function that has a pair of complex poles. Well, we know that let's say our damping in this case is smaller than 0.5, for example. Well, then we know our magnitude plot looks like this, where we've got a peak of -20 log of 2 times zeta. Zeta is your damping ratio. And then we have a drop off here of -40 dB per decade. Okay. And just like I explained previously, the frequency response or the magnitude plot of a transfer function that has a pair of complex zeros will just be the reflection of that plot. Okay, now it looks something like that. Where that is 40 decibels per decade. Okay. Similarly with our phase plot, we know that it's a Markov omega b here. we know that it breaks away approximately at omega b over 5 to the power of zeta, and it joins the negative 180 degree line at omega b times 5 to the power of zeta. Okay, so this, just to make it clear, I'm plotting the phase plot of a transfer function that has a pair of complex poles. So we know it goes up to there. It's negative 90 at omega b, and then it's negative 180 at that frequency. Okay. So the phase plot for a transfer function that has a pair of complex zeros will just be the reflection about that axis. So that's negative 90 degrees and that's 180 degrees. We know it's then going to be 90 degrees there and 180 degrees there. So we can directly draw that phase plot. Okay, that was quite easy. Okay, so now you have the tools to plot any transfer function that you might encounter.